Hey, so today we're going to be talking about exponents, and we're going to be talking about the very basics of it. So here's the basic nature of an exponent. You're going to have a base, that's the big number at the bottom. You're going to have an exponent, that's the tiny number at the top. And what it does is it takes the number 1 and it multiplies 1 by the base, that's 2 in this case, 3 times, because the exponent is 3 times. 1 times 2, 3 times. And that will equal, 1 times 2 is 2, 2 times 2 is 4, and 4 times 2 is 8. So, there we go. Chirp, boot, ta-da. 2 to the third equals 1 times 3 2's equals 8. The rule for computing exponents is multiply 1 by the base as many times as the exponent says to. Here at the bottom we have another example. 3 to the 5th equals 1 times 5 3's. So what I'm going to do is say 1 times 3 is 3, just gets rid of the 1. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And 81 times 3 is 243. And that's how we get our answer. Pretty cool, right? Why is there even this 1 here in the rule in the first place? Well, it's so that it works out for your 0 exponent, which says that any number to the 0 power is 1. Why is that? It doesn't matter what the base is because you're multiplying 1 by that base 0 times. So you're just multiplying 1 by nothing and you get 1. So any number to the 0 power is 1. Just to reiterate, what's negative 10 to the 0? 1. What's 0 to the 0? 1. What's anything to the 0 power? 1. Anything to the 0 power is 1. Cool. The identity property says any number to the first power is itself. Now that should make sense because anything to the first power is 1 times that whatever that number is, right? So 0 to the first power is 0, 9 to the first power is 9, and anything to the first power is whatever that anything is. Okay, now, why does this even matter? Why am I showing you the identity property in the first place? It's for a problem where you have something like this. When you have a problem that looks like this, it says x times x to the third. And the reason you need this identity property isn't to know that x to the first power is x, but to know that x is equal to x to the first power. Do you get it? What I'm saying is that the only reason you'll ever need the identity property is not to go from this side to this side, but to go from this side to this side. See? So n is equal to n to the first. X is equal to x to the first. And we'll see in just a second that this allows us to compute this problem by adding our exponents. Ta-da! And I'll show you how that works. So the product of like bases. If you're following along on your sheet, this is rule number 3. Alright? The product of like bases says that some base to a power times that same base to another power could be the same number equals the sum of those two. So let me give an example because all these words might just be confusing. Let's say we had 3 to the 5th times 3 to the 3rd. That would equal 3 to the 8th. Why? Because we just move this base over, we just move this 3 to the other side, and we add 5 plus 3 gives us 8. Does that make sense? Let's do another example. What would 2 to the 7th times 2 to the 6th equal? 2 to the 13th. Yes. And now let's do one that's a little more complicated. Let's do one that is 7 to the 9th times 7 to the negative 7th. Okay? Do you see it? Now, even if we don't know what a negative exponent is yet, we know that we're just adding 9 and negative 7, right? 9 plus negative 7 is the same as 9 minus 7, which is 2. So on this other side, we just get 7 squared. Okay? That one's a little bit tricky. Now, here's an interesting problem. What if we have 3 to the 6th times 2 to the 5th times 3 to the 8th? Well, you might say, oh, we just add these three numbers up. And if that's true, then what do we have as our base? That's the issue. You need to have the same base. That's what like bases means. It means the same. So this 2 to the 5th just comes along for the ride. We just move it to the other side. What about our 3's? We combine them by adding the exponents, right? So 3 to the 6th plus times 3 to the 8th will be 3 to the 6 plus 8 is 14. Ta-da! And there is your magical answer. Okay, now let's do an example that would be like something that you see on a very difficult problem for product of like bases. I'm going to have two numerical elements that we're going to combine, and then I'm going to have two different variables that we're going to combine. So this is our really difficult problem right here. And this problem is similar to basically, do you know this worksheet I gave you, the properties of exponents worksheet? Basically 1 through 10 are just like this problem I'm about to show you. Okay? So, say you have 2 times, or 2x to the 5th, y to the negative 3rd, times 3, y to the 7th, x to the negative 7th. What I'm going to do is just reorder the way that I'm multiplying this, okay? So I'm going to say that that's equal to 2 times 3 times x to the 5th times x to the negative 7th times y to the negative 3rd times y to the positive 7th. So what I did is I used the associative property of multiplication to say it doesn't matter what order I multiply these guys in, and since it doesn't matter, I'm going to make it convenient for myself and put my numbers next to each other, my x's next to each other, and my y's next to each other. I just have to sort it out that way. Okay? And then I say 2 times 3 is 6. X to the 5th times x to the negative 7th is x to the negative 2nd. Okay? That's because 5 minus 7 is negative 2. 6 x to the negative 2nd. And then finally we have here y to the negative 3rd times y to the positive 7th gives us y to the 4th. And that's our answer. That's as far as you can take it. That's as far as you go. Okay? And yes, that method will work for all 10 of those problems. Okay?